Sir, hope I am audible, sir.
Yes, sir.
Yes, sir.
Yeah. So, dear participants, with a energetic way, we are leading to our second session of the day 2 on the topic concept of disaster management and vulnerability. The expert is Dr. S. Sivaganesh from Hong Kong Polytechnic University, Hong Kong. A short brief about Dr. Sivaganesh, sir. Dr. Sivaganesh Selvaraj is a research assistant professor in the Department of Civil and Environmental Engineering at Hong Kong Polytechnic University. His research focuses on steel structures, cold form sections, structural reuse, and FRP applications in constructions. He has H indexed of 22 and 42 peer-reviewed journal publications and multiple research projects. He completed his PhD in structural engineering at IIT Hyderabad, where he also pursued an MTech integrated with PhD. His academic journey includes postdoctoral research at IIT Hyderabad and Hong Kong Polytechnic University. He has received several prestigious awards, including 2024 Alumni Award from IIT Hyderabad, the YDK Young Researcher Award from USA, and ATCO Design Award from India. Dr. Selvaraj has successfully secured research funding, such as the General Research Fund of HKD 990228. He has an active mentor for PhDs, masters, and undergraduate students, and serves as a reviewer from top-tier journals like ASCE and Elsevier. With this short introduction, I request Dr. Selvaraj to continue the speech. Selvaraj, sir, the meeting is open to you.
Thank you,
There
sir.
is some background noise.
Yes. Let me inform them. So, 1 minute. Okay. Thank you, sir. Thank you for the kind introduction.
Thank you, sir.
Are you able to see my screen now?
Yes, sir.
Okay. So, thank you, sir. Thank you for the kind introduction and the opportunity. Um, my topic of presentation today is concept of disaster management and vulnerability. This topic is, it is a very generic topic which everybody is aware of, and they all know what is a disaster, which they are facing every day. They come across news. But the thing is, I will split this presentation into mm, few parts. First, I will talk about overall management problems, then vulnerability, uh, the engineering weakness. The meaning of vulnerability is weakness. So I'll talk about engineering weakness, then potential solution and implementation strategies to overcome this, this disaster. So most probably, I will go through the climate disaster, that we are facing through. So, as I said, this presentation will have two different aspects. One is fully focused towards climate disaster, but how do we address this climate disaster through engineering strategy? That's what we are going to do. So, what are the takeaway from this lecture? We will, first, we will see what is climate disaster. Is it natural or unnatural? And how are we responsible to it? And how do we manage the climate disaster and prevent it? How consistent field is responsible for climate disaster? We all, I, I assume most of you are from civil engineering background, so we should know how are we responsible to this, climate disaster, and what are the barriers towards controlling or preventing it. And I will also explain the potential plan for integration of stakeholders like industries, government, and public. So let me put this first. I asked this question myself. I work in these various fields: structural design, colform steel design, wall panels, composite design, CFRP, and retrofit research. But how am I responsible for climate disaster? This is the first question that comes to me. Everybody these days, they all talk about electric vehicles. They think electrical vehicle can save the world from big climate disaster. It can control the carbon emission. It can control the uh, the global warming. They all think that. But let's see which industry is polluting more, which industry is taking more natural resources, and which industry is causing more waste. So this disaster management is very simple. So once a disaster happens, we respond to it and we recover and we try to do the preventive technologies. Then we prepared for it for the next disaster. But these are the very common things we know, but we don't know how to cut this. We don't know how to avoid this disaster. So what we know the cause of disaster. We know how to prevent it, and what we don't know, how to avoid, how to control it, how to minimize the effect, and barriers of implementing these strategies. We don't know how to do. We know all the management things, but we are not still aware of, how to put things together and integrate various stakeholders and make it happen. So if you do that, then we can break this, cycle of, preparedness and again falling into disaster and preparing and coming back doing this. This is what we want to see today. Let's see who is responsible. Let me play a video, short video. So the disaster can happen in many ways: cyclone, drought, flooding, earthquake, and a big fire. We can have cyclones and big winds. All these things happens. So due to this, the major thing that happened is financial loss. Every country will go through a financial cycle, financial loss. So what happens, mainly the people from the affected area move to a safe area. Most likely they come to a city, they migrate to the city. So when they migrate to city, the whole population contained to a small place. Then again a big disaster happens, then everybody get affected. So now they are in a simple a small zone. Then again pollution will increase. Again big disaster occurs. They all go to this cycle, go go to this cycle. So now we need to understand this risk. So to under to we need to act rapidly, rigorously, and regularly. So it comes from various people. People should act, industry should act, and government, public, all should act together. And we should have an integration plan between us. So we should do the analysis. We should come together and act together. So that's what we are going to see how. So first, it comes from education. So we all go through the education. We need to create awareness among the people about how this doesn't happen, who are responsible, how do we overcome it, all these things. Next, we should have a data for this disaster. Who is responsible? Which industry is causing a problem? Where is the root cause? How do we overcome it? Where do we take the measurement? So it all comes from various aspects. Researchers, academics, and public all should act together. Again, you can see that it's a overall problem. Now the question is, who takes the main responsibility for this disaster? That's a big question. So despite whoever it is, we need to prevent it. So now let me put this question, sir. Ramesh sir, you can turn the mic to the audience. Let them answer to this question. Which engineering field is responsible for the climate disaster? Who has more responsibility, and who needs to act? Let me put this question. Let some audience answer. I have given six options: electrical, mechanical, construction, paper and cloth industries, petroleum industries, chemical mineral industries. Let some audience answer. What do you think about this? Do you think electrical engineering is the main cause for this, because they are the one who are developing now electrical vehicles? They think they can control the global warming in the mechanicals, construction, paper. Who do you think? We
All
we get
branches, sir.
huh? All
All
branches.
branches, sir.
So we all are responsible. So let me put into this with the further very much classified aspects. So here you can see how much we are all contributing to the climate disaster, or how much we are pressuring our natural resource. So mainly, one is electrical and heat production, that is there, but there are three more things you need to consider: manufacturing, construction, buildings, and waste. Waste, most waste comes from construction waste. The construction waste is not able to, we are not able to recycle it. We have a solution like recycle concrete, but still it has to go through a cycle of processing that again need lot of resources, energy. So again we are using our natural resource somehow for that. So it contributes to big amount. So the latest global resource outlook says that this comes from United Nations program. They say that construction engineering industries contribute to 59 percentage of natural resource extraction. They take metals, minerals, gravel, sand, crushed rock, water. They take everything, but finally they give back waste. That's what we are doing. So I feel as a civil engineer, we should take more responsibility towards this. If you look at the news every day, you can simply read that you can directly come to a conclusion that construction industry emits higher amount of CO2 compared to any other industry. The cement industry, the steel industry, they all emit lot of CO2. So coming to this climate disaster and carbon neutrality, is construction industry contributes 31% of CO2 emission coming from this various aspect during construction, manufacturing process, other industries, transport, residential, all this all come to this. So this is the process of construction. This is upfront carbon. That means during construction stage, and this is happened during a building in service. This is final stage. So we have this big issue that we need to overcome. And this is the data I collected for my own paper. Okay, I have published one paper on this circularity in construction, where I mentioned that all these countries have proposed a idea for controlling the waste from construction, but none of them have been successfully implemented. We are trying to implement, but we don't know the exact solution. We don't know how to integrate various stakeholders in this problem. So the contents of this presentation: what is circular economy for circular economy for construction and its history? What is the necessity of circular economy construction? Why it is called circular plus economy? What are the management barriers? What are the technical barriers for implementation, and how to solve, and who are leading in implementation? And the contents of this presentation is from my following research paper and its references. This is the paper we published last year, on title, recommendations for implementing circular economic construction, direct reuse of fuel structures. We have given some ideas for how do we do that. We also proposed potential strategies which is accepted by the government of Hong Kong. And what is circular economy? This strategy is well known for many decades, at least since 1960. We are aware of this method called circular economy, but the solution is not there. So far, what we are doing, we take the materials and we build, and we, after service life, we waste it. But we wanted to reuse the material, not just repair and maintenance, not just recycle, but we want to do reuse, direct reuse. That's what we are looking for. So here is the circular economy. So instead of having a linear approach, we should have a circular approach. This one, you see, building materials, we do the construction. After service life, we recycle it and waste it. But we wanted to have a repair and maintenance, and instead of demolition, we should do the disassembly, and we should reuse it again. That's what we should do. See, here is the approach. The need for a circular economy is there is no waste in the natural ecosystem. Waste by one organism will be useful for others, but civil engineers is making most of the waste. Metal extraction increased by 300% in the last 5 decades. In 5 decades, the material requirement has increased by 300%, and the per capita material demand increased by 65 percentage, and this will lead to further 18 tons in per capita, 18 tons in 2060. We don't know whether we have material for that or not, and considering it takes the maximum share, so we need to have a fundamental change in the material production itself. So we should have a direct reuse method rather than simple recycling. Okay, who brought this approach of circular economy rather than take, make, waste approach? We call it as TMW approach. Take, make, waste approach. Who brought this idea? The idea was brought by two authors, in 1982. One is the Alan MacArthur Foundation of UK. Walter R. Shadhell is an architect. He brought this idea, and a US architect also brought this idea of cradle to cradle, remaking the way we make things. He wrote a book on this idea. The idea is there for a long time, and we still don't have a implementation plan, because the construction industry has uh, several stakeholders: governments, public, clients, construction industry, material industry, and we also have a supply chain. If if there is any barrier between one stakeholder, there will be a huge supply chain problem that has to be solved. So, okay, this is what the approach we are using now. Take, make, up approach. From here, we are going to a recycle or reuse or remanufacturing approach. This is what we call as circular economy. And if you do that, we will get more business opportunities, because if you do reuse, there will be another opportunity for the industry. If you do the remanufacturing or refurnishing, before remanufacturing, you'll do the testing. So testing means the NDT industry, non-destructive testing industry, will also get benefits. So there will be a lot more opportunities, lot more startup ideas will come in from this approach. And general barriers are the perceived risk in specifying reused materials. Who, which client will take the materials? If you demolish a building, which client will come and take the reused materials? There is a risk, and a lack of reuse market and supply chain. Nobody will come and do the purchase for that. And cost, reuse could be more expensive. The composite construction, they are kind of engineering problem. You cannot demount the structure if it is composite. Then time constraint, which favors demolition over deconstruction, because deconstruction will take long time rather than demolition. Then inaccessible or irreversible joints. Whatever the joints we are having in the construction, they are of monolithic. You cannot simply demount them. So it takes a lot of time. So it's engineering problem. And what are the management barriers? Perceiving risk of specific reused materials. Our current construction practice is not suitable for reuse, mainly based on concrete. And we don't have data about a material reuse. We don't know how long the material has been used. Only if we can recalculate the remaining strength of the material. Then how long we can reuse in future, how long we can reuse, and how many times we can reuse. What is the relationship between number of reuse and the number of amount of load we can apply? We still don't know. We don't have a method for method for reuse design, or we don't have a limit state of reuse. And degree of confidence, we don't have confidence in the client for reuse. And we don't have a system called material storage, where we can get materials for reuse. No awareness about the reuse market, data about availability of the reuse markets. And engineering problem, first thing is the cost. The reuse can be expensive. Then the composite construction, because the structure is monolithic, time constraint, and inaccessible or irreversible joints. So far, I explained you about who is responsible for climate disaster, who contributes more, and engineering problems, and who can control it and how we can solve this. Now I'll open another presentation where I will explain the technical ideas that we are proposing. Okay, one second. So here I will talk about mainly into the construction industry, how we are going through, how the construction industries bring in new revolutionary ideas, kind of fundamental change in the uh, processing itself to uh, support the climate change activities, like controlling the CO2 and carbon neutral activities. So okay, let me explain this very clearly. First we take the materials from the resources, then we process it, then we do the design, we construct it, then we do the life cycle cost analysis, do the service life, then we demolish it, then again it goes to recycling, and it goes to the material again. But the problem is, when you do the recycling, you again need a lot of resources. I mean, energy for bringing a new material. So this again cause some kind of uh, carbon emission. So that will again lead to climate disaster. We are going to, yeah, emit lot of CO2 for that. So instead of this approach, we should bring to this approach. This is called in a very simple. We have material. We should do DFDR design. That means design for direct reuse design with interlocking connections. We will not have a simple uh, traditional method of connections. Rather, we will have a interlocking connections. The members will be connected to each other, and it can be demounted easily. Then we'll have a prefabricated construction. Then we'll do the time cost benefit analysis with environmental benefit. Then rather than demolition, we do deconstruction. Then we segregate the members, just certify it, doing a testing. Then it comes to the material. Because of this change in the testing and certification scheme, we will have a many more new business ideas. How we can have a new industry for testing, one more industry for testing, one industry for deconstruction and certifying it, and storage, supply chain. We can all have a new startups, but it comes from a integration of civil engineers, publics, clients, and construction industry and the government. They all should act together. So ultimate impact will be reduction in upfront carbon emission up to 50% due to significant reduction in the material extraction. If we use this approach, we will not be relying on the natural resource. So we are controlling the climate disaster that is going to happen in future. I told you in the beginning that we are expecting to have 60 percentage increase in the material demand that can be completely avoided by using this approach. So this is the approach we are using now. Take make waste. How to change from our conventional linear approach to circular approach. Actually, there are many challenges and barriers, but still we can uh, achieve this. Let me put this how. I already separated this into two. One is engineering risk and management risk. Risk in reuse of structural components, because the structure is already used. If we demount here and reuse it, there'll be a problem of strength. We don't know how much strength this material can take. This may be new one, so it can take up to its yield strength, but this one may not be. So we need to have a limit set of reuse. That can happen by certifying it. We can overcome. Then confidence. We need to create a confidence in the clients. Then managemental risk, lack of reuse of markets, supply chains. Who will buy from this deconstruction? Some industries would come forward and set up a big plant where they can segregate the members and sell back for a new construction. So that we don't need to rely on a river sand, we don't need to rely on the water, we don't need to rely on sand or aggregates. We can reuse this whole thing. Then preparing the use structural members for reuse may be expensive. Yes, it can be expensive because we are changing from demolition to deconstruction. But we already have a manual for reuse. The European Union has published a report, for how to deconstruct the single story buildings and reuse it again. So deconstruction of the building and preparing for relocated reuse might be expensive. So what we can do, reuse of social members at the same site with the same modified configuration will be cheaper than the relocated reuse. That can be done with this specification. The non-availability of the standard guidelines based on target investment analysis for each structural material is an important barrier in business model creation. We still do not know how much the impact of each material, how many members we can reuse. If it is a concrete, it may have some corrosion, it may have some deterioration. That can be done only by testing. We should do testing. And we can see from here, solution, fully new structures. There are two ways of creating a limit state. One is fully new structures designed for reuse of components, make the new condition demountable. And new structures using used components, design of reused components, use higher factor of safety. If the factor of safety is 1.5, you make it 1.75 or 2, then we can reuse it at least one more time. Then at least we can the save the next set of material that is coming for construction. And here you can see the delay in construction due to complexity and irreversible nature of structural connections. The connections are highly monolithic. You cannot separate the beam column. You cannot separate beam and column. You cannot separate the column and foundation. How do we do? But we have a standard, ISO standard 20887, sustainability in buildings and civil engineering works, designed for disassembly and adaptability. They have principles and requirements. They have a very clear idea on how to design a structure. So the connection and exchange methods are mostly monolithic. Therefore, they it's not possible to demount it. So what can do? It further delay in disassembly will favor demolition over deconstruction. Even if it is reused, the cost for refurbishment will be higher than the original material because they are not designed for reuse. So what we do, we develop a principle of reuse by having all these approaches. The, the future construction should be ready for future adaptability. Okay, the definition is given here. The fixity, expandability. The fixity means boundary conditions. Fixed end or pinned in whatever. Then expandability, it should accept the future, it should accept the future a structural expansion. And refurnish I mean, which means even if the functional characteristics change, it should accept it. Then the structure should be very simple. We need to standardize our structures. We cannot have whatever member we want. We have to have standard members that can be reused for next purpose. Then versatility, convertibility, and accessibility. Finally, after all, we should also have a NDT based solution. That means non-destructive testing. So the member can be scanned and the data can be stored for checking its quality. Then we can certify it. What is the remaining strength of this member and how many times it can be used, how long it can be used. Understand? So one can ask a question, sir, how is this possible? It is possible because there is something called material passport. What is that? Material passport. Like we all have a passport, right? Wherever we are traveling, they put a seal. Whenever you enter a new country, they put a seal. Okay, they'll give you visa before entry. That means you are certified to enter. So likewise, we can also have a certification scheme for a building, like material passport. So the material passport will contain how long the material can be reused, how long the structure is already reused, what was the climatic condition of the reuse, and what is it material strength, when was it purchased, who was the purchaser, who was the client who constructed it, and what are the the materials involved in the construction, what type of boundary condition was used, was there any accident in the building. All these information will be available in this material passport. So that can be that data can be directly used for this, creating a confidence in the builders. And the more importantly, uncertainty in the business model. So The question is how to calculate the building future using life physical assessment. The question is, and life cycle cost analysis. When the structural members of different ages in the same building, who will take the responsibility? That's the question. Then who takes the liability when the damage or accident occurs in a mixed reuse environment with the structural members from various industries? How to calculate the insurance premium cost of a new building with used structural components of different cycle and quality? Now we have a different problem. That's why industries are not coming forward to coming forward for a fundamental change. We are going the same direction. We taking the material from nature and we are using it and we are wasting it. So what is solution for this? Let me put this problem in example. This insurance premium cost. Now all the buildings, big buildings, big industries have insurance against their properties. So if they already reuse of if they constructed the whole building from the reuse from the reuse, and if those structural members are from different industries or different places, how to calculate the insurance premium? If it is a new material, the industries will come, the insurance company will come forward to give you insurance. But if it is of already a used material, they will not come forward to do that. So there's a problem here. So that can be done. I'll tell you how. I have solution for that. We are proposing some idea for that. And lack of design source, mainly we don't know how to design the components and structures for direct reuse. So how many times a structural member can be reused? What is test limit that the structural member should be loaded at a first reuse, second reuse, and third reuse, and so on? The relation between stress level in the structural member and number of reuse cycles. Because the first time we can go up to plastic moment, but second time it's already yielded. Then how can you reuse? Is that possible? So we should have a different limit state called different limit state called limit state of reuse. Only then we can control the climate disaster. Otherwise we are going to face it in future. Okay. And lack of principles towards circularity and consensus design sustainability. How to design the new structures for air reuse? How to design the new structures using used components? What materials to choose for reuse consumption and material durability? These are all a very big questions which industry don't have answer. That's why we are in the linear approach. So far we discussed about barriers. So now let me give you an idea. Let me put a case study on steel structures. Okay, answer for where to begin this circular economy. If you want to use the circular economy approach, and if you want to come out of the climate disaster, if you want to avoid the climate disaster, or if you want to prevent the uh, climate disaster from occurring, you need to change, you need to have a fundamental change in the construction. That means you need to go for a sustainable material or highly durable material, that is steel. Okay, so you can see from here maximum safe profitable distance for each material: concrete, brick, and steel. The steel can travel up to 4,000 km without any deterioration. This means if you transport a steel member from one place to other place for reuse, the member will not have a significant strength erosion, whereas concrete can transportable up to only up to 240 kilometers. So in this case, the steel can be the winner for this. So this is a two different approach of steel making, and the minimum price of new steel is 261 USD. So what we can do: fabrication, construction. This is structural member fabrication, construction, end of service, do entity testing. If it is safe, and what do you do? Safe, do the deconstruction, direct reuse, raw material and energy can be saved, and testing and certification. Again, go for a construction. Once the construction stage, end of service, testing, deconstruction, again it comes to construction. That means reuse cycle. But this is what the idea we are recommending for a reuse approach. But if it is unsafe, after a construction, if you find the structure is unsafe, then you can directly go for demolition, recycle, and go for a full reuse. That means we can take the steel again here and put it for a arc furnace steel method of steel manufacturing. Still, you can save a lot of money from here because you are using reused steel for new steel. Okay, so minimum steel will be 58. So 261 minus 58 will be $203. This much dollar can be used for transportation of a member, quality assessment, and cost and benefit profit. And this also can be a profit for engineering industry. The reuse of steel is much more cost efficient than other materials. So the steel can be one of the highly sustainable materials for climate change climate change disaster prevention. Okay, and let me put this, the method called uh, design for deconstruction reuse. So far we all gone through limit set of ultimate, limit set of cracking serviceable limits, all these things. But now we are coming up with a new design method called design for deconstruction reuse. This is only for achieving the you know uh, achieving the prevention of uh, prevention of climate disaster. This is very simple. The construction should accept the member from previous review. That's it. How do we do? We can have interlocking connections. The connection should not be monolithic, rather it has to be interlocking. Okay, the interlocking connection introduced in DFR principle, DFDR principle, the model that joins two or more structural members by a simple locking mechanism. This is very simple. Okay, the DFDR will also can also have a minimum number of bolt, but eliminate welding. No welding. If you weld it, you have to break it. Then again you have to go for a demolition. Again full waste. So rather than we can have this strategy. So in this strategy, what we can do, this is the approach I'm proposing. First is material from natural resource. We are having a DFDR approach, constructing a building and doing after the service life of the building, we are having structural identification system. This means we will identify which member can be reused or unused. Then we will do the disassembly process, testing. We'll reuse it and it'll come again for a supply. Whereas if it is a damaged one, it'll go for a waste and landfill. That's it. Further still can be reused, recycled. Remember the difference between reuse and recycle. Recycling means we need lot of energy for bringing the material to a consistent stage, whereas reuse means direct reuse. The beam can be directly reused again without any problem, and column can be reused again. The whole members of the building can be reused. I mean, all the components of the building can be directly reused rather than demolishing it. So by doing so, at each stage of this process, we can save this much carbon emission. So by doing at least we can control 50% in the beginning itself. If we use this DFDR approach, we actually complete a survey where we can found that here itself we can save of around 50 to 50 percentage of uh, uh, you know mm, uh, carbon emission. That means yeah, we are avoiding the climate disaster. So integration strategies, as I told you here, there are sorry there are many industries involved in this business. Okay, here I told you that there are many industries involved in this business. Clients, construction industries, public, governments, also testing industries, certification industries, builders, clients, all people. And there's also a problem with real estate makers. But we are proposing a new potential integration plan to integrate the stakeholders. First approach is very simple. You use the DFDR principles for at the production consent stage. DFDR principles. Using all these ideas from ISO standard, we can fabricate the member. Then it goes for building design, then individual member design, individual member model, then interlocking connection. For each member, we should have an interlocking member. Then check for fabrication, whether it can be fabricated or not. Then if it fails, again go for a building change, come back. If it is passed, then we can go for a if it is passed, we can go for a component matching, then BEM model, safe disassembly check. While designing for a construction itself, you need to check for a disassembly check, whether it is safe to disassemble the building or not. If it is safe, go for a construction. Otherwise, rebuild the entire concept until you achieve this. This is the algorithm we are proposing, a small algorithm for construction industries. This is a fundamental change we are making in the initial process itself to come out of a climate disaster. Next, after construction, for reuse again, from the construction, after the construction process, after the building service life, what we can do the preliminary assessment, whether how many members can be reused, how long was structure was in service, was there any accidents in the building, what was the weathering condition, uh, what was the loading condition, all these things will come into picture here. Then if you think the reuse scenery is okay, then we can go for a design for design check for reuse. If it is passed, we can directly come here and uh, do the construction again. But if it fails, we can do the modified safety factors. I told you, right, for reuse reuse we should have a, a limit state of reuse with high safety factor. Instead of 1.5 of, we use 1.5 in limit state, rather we can have it as a 2, so that we can reuse the for consistent we can reuse the components once again for long time. So if it is fail, we can achieve this. But again, after second reuse, we'll do testing, preliminary assessment, fails, scrap. If it is passed the preliminary assessment, do the complete assessment, geometry check, material testing, confirmation to the international codes, documentation, again fail, do the modification, modify safety factor, reuse. If it is passed, go for a little bit of change, again, classify the member in the market center and go for construction. So the cycle keep on coming back, so that the material once taken from the natural resource will never go back to waste. It is always within the loop. So the material is efficiently used. If you have a building once you constructed, the building will never go for a waste. It will always be there. We can keep on reusing it. The only thing is we need to make a fundamental change from the beginning itself. That means we need to have an interlocking connection design. All the members should have an interlocking connection between wall and foundation, and the column to foundation, beam to column, and then the slab to beam. All should be a interlocking connection. That's what the whole idea is. And how the supply chain will support. So far we discussed about technical ideas, but this is a management problem now. Okay, now we need to know where are the buildings, where is the building now. Then we'll do the input output analysis. How much can be the input, who will take it, who will not take it, how much member can be reused, and all these things will come to picture here. Then we'll do the hotspot analysis, which means where the buildings are old. Then there we can set up a new yard for reuse. Then we can have ideas for startup. Then audit team will do the industry. Then government will come into the picture for the policy making, auditors, net present and value assessment. All these analysis will come into picture. If it is really possible for a reuse, then government will make a policy making to implement the scheme. That's what. And the business model. I think this is the first model that we are proposing for, proposing towards a climate change action in the production stage. Who are involved? Producer, manufacturer, fabricator, they all involved. The outcome is products. By doing a DFDR design principles, Then then after doing this, the erector, contractor, developer will come into picture. Then building, who will pay the cost for this? The user. If the client, the end public will pay the 100% of the cost. Okay, the user pays after the reuse sorry, after the service of the building. User pay 10% for demolition. Okay, the user and the owner will come into picture here. Then use and repair stage. During the repair stage, we will do this analysis, time cost benefit analysis. Net present value will be calculated to assess whether it can be demolished or disassembled. Then audit and insurance team provide preliminary assessment on disassembly, whether it is safe to do it or not. Then deconstruction stage. The current recovery percentage may be increased after adopting DFT principle, design principle with interlocking connection. If you use a interlocking connection in the building, your your percentage of reuse would be really high. So at present, more than 70% of building components can be recovered from the strategy and directly reused. Further, at the reuse stage, the product claimed by the scrap trader, and I mean the scrap person will come and collect the products. Then he will put 10% cost for testing and transport. Then user get 20 to 40% take back from the scrap trader, because the scrap trader will pay back to the user rate who paid for the initial cost. So 40% will come into the user. So you pay 100%, but you get back 40% by just implementing this drug connection. Very simple. Then you know this will further increase by implementing DFDR principles. This can go up to 50%, because if the number of members increase, number of reuse members increase, your your the payback will also get increase. Then uh, the stock list will happen. How much can be reused, stock list will happen. Then all these checks will be done by the industry. Then the government will come into picture. Government will have policy for this. Okay, policy for green methods to control the climate change. Then incentive to the owner, incentive to the owner, reduction in annual property tax. The government can give a uh, in, the government can give a reduction to the annual property tax and property stamp duty for the owner by giving incentives. Only if you get some incentives, we will implement the strategy. The clients will come forward to take it. India, we are giving MSME loans, right? Similarly, we can have many ideas to control the climate change. Then incentives to reuse business. I told you, right? We can have many startups for certification, many startups for demolition, many startups for storage yards. So governments can give incentives and loans for new business. So once it is done, then government can also do R&D programs for that. Once this is done, then the reuse link will be activated. So the whole process will keep on happening. Overall, we can achieve the prevention of climate disaster. We can prevent the climate disaster from happening. Okay, so what do we do to achieve circularity construction? Very simple. Develop a simple demountable connections. Okay, reuse decision design methods and NDT design practices, and management strategies for supply chain. We are doing this project in Hong Kong, which will be implemented at the end of 2028. I'm one of the person working in this project. So the ideas are given here. You can see, demount of structural connections. The concept is very simple. If you have a member like this, and it can be demounted, and we can have another structure with the reusable components. These are the interlocking connection ideas we have developed for beam, column, and foundation connections. You can see very simple ideas. We are doing testing now. I'll show you some photographs later this slide. Concluding remarks. I have explained the circularity construction. I have proposed alternative direct reuse circular economy approach, and I also emphasized the how steel structures can be a solution to circularity and reuse concept, and the new strategy for integrating the features of construction and to create a circular economy is proposed. Then a potential take back business model is also proposed. Okay, all these ideas are given in the paper. Okay, now let me go back to the original slide. Okay, we discussed all the ideas now. So now I'm coming back to the original slide where we talked about climate change. So now I'm going to give you the real ideas that are already available, already in practice, which we can take it for a new construction. So what is strategy for adopting circular economic construction? Choice of a material for construction should be directly reusable, steel or steel components. Application of advanced engineering for development of reusable, demountable structural engineering concepts. Automation for fabricating structural components such as prefabrication. Create material storage banks and material passport system. Material certification scheme, which means I told you right, a passport, material passport, like the whole system, the whole history of the material can be given here. Then create a e-commerce ideas for reusable structural components. Mm, I'll play on a video where you can see, where you can see how the clamp will work. This is actually from a Lintopter. It is already available on the internet. You can see the video. The video is playing on how the column and beam is being connected using interlocking approach. You can see that it is simple clamp rather than having a bolt. If you use this approach of connection, you can dismantle the beam and column easily and reuse it back for a new construction, so that there is no waste from the construction industry to achieve a prevention of uh, climate disaster, or to completely avoid the climate disaster. These all these connections are tested against severe loading conditions. You don't need to worry about slips, or you don't need to worry about the load factors. They are very tested. They tested in Hong Kong also. We are doing some testing on these bolts. And this is a countersunk connection for tubular joints. For tubular connections, we can have this uh, countersunk bolt connection. You can see the bolts are tightened from outside for a tubular joints. These are the innovations that we are making towards achieving a you know achieving a prevention of climate disasters, or to avoid climate disasters. It's again a hollow bolt. Like it's a composite construction where you can have no concrete at all. Again, this is a composite construction video from TU Delft. Netherlands have proposed this strategy where they can have a complete demountable connection methods. It's actually for a building plus parking. So some of the demountable connections from various research groups. This is from Netherlands. Again, they developed a beam column connection for direct reuse. This again interlocking connection. This is a interlocking connection between slab to slab. There are two slabs being connected. Again, this is you can see the interlocking connection. They are actually climbing up and doing a testing before the installation. See how the member can be reused. These days we have a drones, right? Drones for uh, drones for visual inspection. So that can be used here to inspect the and scan the member dimensions, if there is damage, if there is any corrosion, or if there is any welding failure. All those things can be measured by drone itself. These days we are using drones for fighting. I mean war, even war fields also they are using drones. So we can simply use the drones for our construction survey also, and material strength testing also. We can do the laser scanning for small connections to to check if there is any defects before reuse. You can see the video where the drones are being used for rebound hammer test. I'll show you how. You can see the drone is flying up and testing the strength of the column. This was actually developed in 2019, but now we have a more advanced system for scanning and assessment. Okay, I can say that European countries are leading in this climate change action. Many industries they are developing different aspects of connections for achieving the climate neutral construction. And this one is a model building they constructed in Dubai during last year World Cup. Uh, World Cup football match was played here, where you can see, the complete stadium called Stadium 974 was built using demountable connections, which means the whole stadium can be demounted and reused back for any other purpose. So the whole stadium was made of steel. They can rebuild this anytime, and the purpose is to build it because stadium how long they can use? They can use for only for few years or few matches. After that they'll use it for some hospital, they'll use it for some auditorium, some other purposes. So the initial stage itself they built with the idea of demountability. The whole connection, all of them were demounted and reused for other purpose. You can found this idea from this link. And conclusions, circular economy is concept is the way forward for sustainable future. It creates model business. It creates more business opportunities and jobs. We need to develop simple and demountable construction methods. Implement a scheme as follows: develop a demountable construction, and do energy testing, and have a material storage banks, which can be a new business opportunity. Then the cycle follows. Again, further, this paper is, we published last year. This has all the ideas of this climate neutral construction. So thank you, sir. Thank you for the opportunity. Hope I given some ideas for future researchers who can start their career in reuse design and development of interlocking connections. Thank you, sir. Thank you for the opportunity.
Yeah. Thank
Ramesh,
you,
sir.
Sir Ganesh, sir. This is Dr. Abdul.
Yes, sir. It's Abdul, sir. Yes, sir.
Sir. Thank you, Sir Ganesh, sir, for your wonderful session. Participants, now the forum is open to you. If you have any doubts, you can ask. Dear participants, the meeting is open to you. If you have any doubts, you can ask.
No doubt, sir. Thank you, sir.
Hello.
Yeah, yes, sir.
Uh, how the maximum safe and profitable transport distance?
Sir?
Sir, you just mute yourself, sir. Unmute yourself, sir. Gopal, sir.
Hello, sir.
Yes, sir.
Hello.
Now you are audible. Yeah.
Yes, sir. Please complete your question.
How the maximum safe and profitable transport distance is
Yeah.
calculated as it is given for concrete 240 kilometer, brick 400 kilometer, steel 4000 kilometer. How it
Yes,
is
yes, sir.
calculated?
Yes, sir. I will give you the reference also. I'll give you the I'll give you who calculated and how calculated, sir. Sir, this was calculated by a researcher from Europe. Okay, and the idea was to concrete is a material that is vulnerable to kind of quick deterioration in terms of vibration loads. If you keep vibrating the during transportation, we will have some vibrations. Those vibrations will cause cracks in the concrete structure, also in the brittle structures. Mainly concrete is brittle, right? So it will have some cracks, and after transportation, if you loading it, there is some reduction in the strength, which was tested by the prefab industry as well. That's why if you look at the uh, de- if you look at the design code of the prefab industry, they have a high safety factors. Okay, and further like steel is a high strength material whose strength is uh, strength is up to 350 MPa. This will not be affected by any transport vibration. This is how uh, those values are arrived,
But
sir.
it will be affected by the environmental conditions.
Sir?
But it will be affected by the environmental condition. There may be carbonation and all these things.
Yeah,
Whenever we are transporting it
sir,
up
sir,
to
sir,
4,000 kilometers.
sir, this environmental things can happen for both concrete as well as steel. That is a constant. That is constant for both. But I'm talking about structural aspect. In structural aspect, concrete may have uh, strength d- 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 strength deterioration due to transportation by vibrations, whereas steel is not. Let me open the document I'm opening. Give me a minute, sir. I'm opening a document and share with you. Is that okay, sir?
Yes, yes, sir.
Wait a minute. Wait a minute. I'm opening the paper and opening the document for you. Wait. CFSS retro. One second, sir. I got the document. I'm sharing my screen. Okay, sir, can you see this link? Can you see the document? Hello, sir.
Yes, sir. Yes, sir.
Yeah, let me also. I have the document. Let me open also. I'm Yes, I got it. Sir, can you see this? The green guide for housing specification. So this I can share this document with you. This shows that the maximum transport distance for reclaimed materials, reclaimed tile 100 miles, but reclaimed steel products it can be up to 2,500 miles. That's why I said 4,000 kilometers. But for concrete and bricks you can see bricks 250 miles, aggregates it's only 150 miles. The idea of reclaiming is given very clearly here. The maximum distance of a reclaimed material. So this is what, sir, I have given you the answer. Hope you are, I should hope you get the answer. Yes, sir. Is there any other question? Hello, sir.
Participants, do you have any other question?
Hello,
Yes, sir. Yes, sir.
sir. Uh, you will make the whole things means it will be increase the initial initial amount, increase the initial amount. Now, how the client will be benefited, sir? Because
Sir,
we are maintaining every step, we are maintaining certification, everything. Now,
no. It is not on the initial stage. We are requesting for a fundamental change in terms of construction. If not now, somewhere else in the future we have to change, because there won't be any material for further construction. We are already destroying our rivers, our big hills. They are all going for construction. So if not now, somewhere in future we have to adapt this change. So better we do it now. We are not going to pay more. You know, the the initial cost may be only 10 to 15 percentage more because of the interlocking connection and due to the steel demand. But when you sell back your reusable
we come
products,
back,
no, no,
sir. We
let
come
me
back
complete,
for
sir, let me complete. When you actually resale your whole building after the service life, you'll get back 50% of the money you paid. So you you're not losing anything. But due to this, we can actually support climate change activities, and we can control the climate disaster. That's what the idea we are putting forward.
okay, sir. Thank you, sir. Thank you,
Okay,
sir.
okay. We had this discussion with the government and also with many industry aspects, sorry, industry experts. They all asked this question: how come industry can take it? That's why we gave them, a nice plan of integration. This one, I think you are able to see my screen now. This idea I explained
Yes, sir.
you.
I
Yeah.
saw that during the presentation also I saw that making this setup, we will maintaining everything. We have maintaining. It will be
Sir,
initially
sir,
we cost
no,
to
no, no,
now.
no, sir, actually, no, no. We don't need to do testing uh, during the first construction. Only things we are going to change the safety factor little bit. Rather than 1.5, we'll make it 1.75 or 1.2. That's it. But because of that small change, we are going to gain lot. Our future generation will get more benefits. We don't need to destroy our rivers. I come from
Ah,
southern part of I come from southern part of India, sir. Okay,
yes,
I
I
yeah,
also that part
I
also,
did
yeah.
I did research on Vaigai River during my undergraduate. So what happens in
Yes,
the
sir,
Vaigai
yes.
River? The Vaigai River starts from Theni district. It comes to Dindigul district, then Dindigul to Madurai, Madurai to Sivagangai, Sivagangai to Ramanathapuram district. So what happens because of the sand mining, there are there are check dams that are getting lowered. That means the whole check dam is getting eroded because of flooding. Once the flood happens, all water goes to river. Sorry, all water goes to sea. We are not able to save the water. So the sand mining should be controlled. I don't say that we should completely avoid concrete, but we need to control it to some extent so that we can save our future. I'm just putting forward an idea for a technical discussion. We all are an experts. We are all responsible for this, you know, future generation. So my, being a young expert and who understand this business, I'm putting forward new idea for some fundamental change. Let the industry come up with a, response. L- Let them tell what are the problems so that we can give the new ideas in terms of technology, but the cost should not be a concern, sir, because that once we invest, that will come back to us in terms of you know magnified return by avoiding the climate disaster.
Yes, sir.
Sir,
Sir,
you can read this
when
paper.
we are sir, you are saying when you are use, that time we have to do for certification, everything at all, no?
Yes, yes, yes. Only
Uh,
during the reuse, not during the
uh,
not
see,
during the initial construction. Yeah.
for example, we will do the certification everything for the client now for resale or
Yes, yes,
company.
yes, 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 yes. Sir, sir,
Whatever resale
sir,
means we have to do the certification. And then,
sir, your voice is not clear, sir.
sir, the client will be uh, do the certification for resale. Correct?
No,
No?
no, 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 sir, sir. Not the client. I give back my building to the uh, seller. Okay, he will buy from me for 40 percentage of the building cost. Then he will do the testing, whatever certification scheme that is required. So he'll pay another 10 or 50% of the building cost. So the cost comes around 60-70 percentage. So from that he again sell back to the new industry at a cost of 70 or 80 percentage. So he gets 10 percentage interest, sorry, 10% profit. That from that 80 percentage, company do some changes or refurbishment, then company again give it to the user for 100 percentage or 120 percentage. So the money almost same, but it can be increased by 10 percentage overall. But the investment will come back in terms of uh, climate, sorry, avoiding the climate. That's my whole idea, sir. We cannot simply telling that the cost is increasing every year anyway. If we don't do also, if we don't reduce also, the cost for sand, the cost for cement, cost for steel is increasing every year. It is going high. It is going, it is actually increasing in terms of skyrocketing. So better we use the old materials and use it at least for one more time. We can save the nature at least.
Okay, sir. Thank you. Thank you.
Okay.
Participants, any more queries?
Any more discussions?
So
I would say.
likewise,
I
Yeah,
would say it's a.
discussion.
I would. Yeah,
Yeah,
discussion. Yeah,
discussion. Any
yeah.
more discussion?
Let them. Let them ask any questions. Let's let us discuss.
Participants.
See, let me tell you a small example. You all think that the EV, electrical vehicle, can change the entire business or entire world by controlling the global warming. But EV is not the only idea. Construction industry also should put some effort to that, because we are wasting a lot of construction waste from old buildings. So we should also put some effort. Where is the we are not having any change. The industry is still the same. Maybe we are including new structural members or new things, new design aspect, but there is no change in the uh, fundamental idea of construction. We are still taking the materials from nature. That has to be changed. We are not changing it anywhere from.
yes, sir,
That's
yes,
the
sir. Because,
yes, yes, yeah.
yes, sir, yes, I understand. But my thing is, uh, this idea can be benefited for a common man like that. That's why I'm asking.
Sir, it will be beneficial, because if not now, future, your grandkid will use the idea, because there won't be any material, there won't be any m- mountain for aggregate, there won't be any river for river sand. If we keep going in the same direction, the time
Yes,
is now
yes,
to change. Yeah, that's why. Now if you
yes, yes,
see
sir.
Hong Kong or China, they are using a volumetric construction. That means they are building blocks, and they are just putting one after other, and they're going for a tall structures. They are not fully relying on concrete. They all want faster construction. They all having a kind of a container type of office buildings. Very fast construction. They are going up to 30 floors now. I'm living in Hong Kong. My next building is 30 floor. It is purely made of steel.
Okay, sir.
Uh,
Okay, sir. Thank
yes,
you.
yes.
Thank you.
Any more discussions, participants? Uh, just a minute, sir.
Okay.
I request all the participants to switch on your camera to have a photo session with the chief guest, Dr. Selvara, sir. Participants, kindly switch on your video. Sir, you can unshare, sir. And
Yeah.
so that
I stopped my screen.
Siva Ganesh sir, very excellent lecture you have done, sir. Thank you very much for sharing the very useful disaster management related buildings and mechanisms. Everything, it's very much wonderful, unparalleled to anything. Thank you very much, sir.
Really, sir, it's a very useful session for us. Thank you so much, sir.
participants, I request you
Sir.
to
Thank
switch
you.
on your video so that we can have a photo session, sir. எனக்கு இங்க வர மாட்டேங்குது. சிவகணேஷ் சார் உங்க ஃபேஸ் கொஞ்சம் விசிபிள் இல்லை, கொஞ்சம் லைட்டா.
Okay, now?
Yeah. Thank you, participants. You can switch off your videos.
Thank you, sir.
On behalf of K.S.Rangasamy College of Technology, Department of Civil Engineering, I thank today's chief guest, Dr. S. Sivaganesh, who has been working in the Hong Kong Polytechnic University, Hong Kong, for his wonderful presentations on concepts of disaster management and vulnerability, and also he has explained the our in detail as a 2 parts: the cold form section buildings, steel structures, built-up column sections. Everything is explained in a clear way. Thank you very much, sir. In spite of your busy schedule and a very late night there in Singapore now, Hong Kong, you have given a wonderful session to us. Thank you very much for accepting our invitation and being with us. I thank all the participants who have joined today. Thank you, sir.
Thank you, sir. Thank you for the invitation also. This is a good opportunity for me to discuss with many experts from different field.
Yes, sir. Yes, sir. It's really very useful to us, sir. Thank you very much, sir.
Thank you very much. Okay.
Thank you, sir.
Sir, shall I disconnect, sir?
Yes, sir. Yes, sir. You
Thank
can
you.
discount, sir.
Thank you
Thank
so
you.
much, sir.
Thank you, sir.
Thank you, ma'am.
Thank you, sir, giving the opportunity. Thank you, sir. Thank you so much.
Thank you. Thank you very much. The meeting has been officially ended. You can wind up now, dear participants.
Okay, sir.
And the
Thank you, thank you.
feedback link will be enabled at the end of the day on day 6th, that is on 22nd February. Through Atal portal, we can able to put the feedback.
Okay, sir.
Okay, sir. Okay, sir. Thank you.
Thank you.
Thank you.
Okay, sir. Thank you, sir. Thank you, sir. Thank you.
Thank you, sir.
Thank you, sir.
Thank you, sir. Thank you.